Right now, inside the phone in your pocket, dozens of chips are talking to each other. Not over Wi-Fi, over tiny copper wires, using three little languages, I2C, SPI, and UART. By the end of this video, you will be able to read all three. Here is the cast. In the middle sits a microcontroller, the brain. Around it, the helpers. A temperature sensor, a display, flash memory, a GPS module. The brain needs readings from the sensor. It needs to push pixels to the display. It needs to save files to memory. All of that is chips talking to chips, and it never stops. The question is how they do it. Strip it down to first principles. A wire carries a voltage, and at any instant that voltage can only be one thing, high or low. Call high a 1, call low a 0. That is a bit, the smallest possible message. Now toggle the wire over time and you can spell anything. These 8-time slots spell the byte for the letter H, one wire, one bit at a time. Engineers call that serial. But there is a catch, and it is the key to this whole video. The receiver has to know UART to look. It samples the wire at what it believes are the centers of the bits. Watch what happens when its sense of time runs just a little slow. Every sample slides a little further off center until it is reading the neighbor's bit. Same wire, same signal, and H arrives as P. Every serial protocol is an answer to one question: how do two chips agree on time? There are exactly two honest answers. Answer 1. Run a second wire that carries the beat like a metronome. Sample on every tick. That is called synchronous, and it is how SPI and I2C work. Answer 2. No clock wire at all. Agree on a speed beforehand, and use tricks to stay lined up. That is asynchronous. That is UART. Let us take them one at a time. UART first, the oldest and the simplest. 2 chips, 2 wires. My transmit pin feeds your receive pin, and your transmit feeds my receive, so the wires cross. Both chips also share a common ground, so they agree on what 0 volts means. And notice what is missing. There is no clock wire anywhere. Both sides are flying on trust. So how does the receiver stay lined up with a frame? The line idles high. When the sender drops it low for exactly 1 bit, that falling edge is the starting gun. The receiver sees it, starts its own stopwatch, and samples the middle of each of the next 8 bits. A stop bit brings the line back high, ready for the next one. Small detail. UART ships the lowest bit first. 1 start, 8 data bits, 1 stop, 1 frame per character. That stopwatch only works if both sides count at the same pace. The pace is the baud rate, bits per second, agreed on in advance by both programmers. Here both sides run at 9600 baud, and hello comes through clean. Now the receiver expects 115,000. Same wire, same signal, and every frame shatters into garbage. One more limit. It is a private call. 2 devices ever. No more. Protocol 2, SPI, takes the opposite deal. 1 chip is in charge, the controller. The chip it talks to is the peripheral. The controller generates a clock on its own dedicated wire, and every pulse says, sample now. 2 more wires carry data, 1 in each direction, and a chip select wire tells the peripheral it is being spoken to. No stopwatches, no guessing. If the clock slows down, everything simply follows it. Drift is impossible. An SPI hides something elegant. Each chip holds its byte in a shift register, a row of 8 cells, and the 2 registers are wired into one big loop. On every clock tick, every bit takes 1 step around that loop. The controller's first bit slides across to the peripheral, and the peripheral's last bit slides back the other way. After exactly 8 ticks, the 2 bytes have traded places. Sending and receiving are not 2 operations, they are 1. Because the clock removes all guesswork, SPI is fast. Tens of megahertz is routine, perfect for screens and memory cards. But look at the cost. The clock and data wires are shared. The chip selects are not. Every device you add demands its own select wire and its own pin on your controller. 1 display, One card, one flash chip, one converter, and you are already at 7 wires. Pins are precious. This is the SPI tax. Protocol 3, I2C, is built to fix exactly that. 2 wires total. SDA carries the data, SCL carries the clock, and every chip on the board hangs on the same 2 wires, like a party line. Sensors, clocks, displays, memory. Over 100 devices can share one bus, and it still costs your microcontroller just 2 pins. But on a party line who is being spoken to, names, every I2C chip has a 7-bit address baked in, and every conversation starts with the controller broadcasting one. Each chip compares it to its own. Here the controller calls hex 48. The clock chip ignores it. The display ignores it. The temperature sensor recognizes itself and answers with a tiny pulse, and acknowledge that says, "I am here, go ahead." No select wires, just names. One last trick makes this safe. On I2C, no chip is ever allowed to push the line high. A chip can only pull it low or let go. A resistor gently floats the line back up when nobody is pulling. So even if 2 chips talk at the same instant, they can never fight and never short the bus. But watch the scope. The line falls fast and rises lazily because that resistor has to recharge the whole wire. That lazy rise is the speed limit built into I2C. So here is the scoreboard. UART, 2 wires, no clock, everything rides on a shared stopwatch, and only 2 devices. SPI, fastest by far, talking both directions at once, but a select pin for every single device. I2C, 2 shared wires, over 100 devices, a few megabits at best, one direction at a time. Nobody wins. They are 3 different trades between speed, pins, and simplicity. Which is why real devices use all 3 at once. Take a smartwatch. The GPS module streams little text sentences a few times a second. Slow, steady, 2 devices, UART. The screen needs a fire hose of pixels, SPI, and the sensor crowd, heart rate, motion, temperature, each sends a few bytes now and then. Perfect for the shared party line, I2C. You match the language to the job. And none of this is hidden. On a Raspberry Pi, all 3 languages live on 140-pin header. GPIO pins 2 and 3 are the I2C bus. 14 and 15 are the UART. The serial console you can literally type into. 9, 10 and 11 are the SPI bus. Wire a sensor to those pins tonight, and you will be speaking one of these languages before bed. 3 languages, 1 idea. Moving bits over a wire takes an agreement about time. UART agrees in advance. SPI ships the beat on its own wire. I2C shares that beat and adds names. Next time a gadget just works, remember, under the glass, 3 quiet languages are doing all the talking. Thanks for watching.